morning, one and all. The subject name is compiler design. Previously, we have taken some of the concepts which are related to this one. And another topic is that is loops in the flow graph. This is also one of the notation which is used in the optimization process while implementing these flow graphs. So what are the various loop structures that are to be occurring? A graph, we know that a graph consists of collection of several nodes. That is called as flow graph, and transitions from one node to the another node. So it is generally used a representation for the intermediate code generation purpose, and this constructed by the algorithm we are known as code generation algorithm. In this, nodes are to be represented, that is a flow graph contains several nodes, and another one is edge is to be available. So this edge is used for the communication purpose from the one node to the another node. While implementing this flow graph notation in case of this compilers, that is intermediate code representations, we are going to use a notation that is dominators. That means a code is to be dominated. What is the code domination? So for example, here a node D is to be available, which dominates node N. Then from initial node of the flow graph to N, and it goes through some D. What is the initial node of the flow graph? That is to N, and goes through the D. Here node D is dominating the node N. So this is denoted by a node structure, that is D dom N. D dom N. We will see with an example. Here every node is to be dominated by itself. That is one of the property. And the entry of each loop dominates all other nodes in the loop. Whatever the entry of each loop has some entry and it exits. So every entry of that loop is to be dominating the remaining and all the nodes which are available in the loop. For example, this is the graph which is called as flow graph. This is called as flow graph, and we are going to obtain a dominator tree for the flow graph. So we know that dominator means a node is to be dominated with the other node if every path from initial node of the flow graph to the N goes through D, then only we can say that it is dominated. D dominate N if and only if every path of initial node of the flow graph N goes to the D. That is if that property, that condition is satisfied. If that condition is satisfied, then this node D dominates the node N. So that is to be represented as D dom N. Here D dom N. With an example, we are going to say here there are nodes which are represented with numbers 1, 2, 3, 4, etc. up to 10. And we are going to represent this node structure with the D dom N, where 1 is to be written, and in the initial node is what? Here, what is the initial node? Node 1. So that is the node which is the dominating remaining all other nodes of the flow graph. Since it is the initial node, it is going to dominate all other nodes. So node 1 is to be dominates every node, and node 2 dominates only itself. Every node is dominating itself, that is, and the control is reaching to any other node. If the control is reaching to any other node, and then that path begins 1, 3. So here node 3, node 2, what is the node that is to be available? So that's why here node 1, node 2 is to be considered, node 2. Whereas node 3 dominates remaining all but 1 and 2. So that's why here a path that begins 1 and ends at 3. the path that begins at 1 and ends at 3. So that is the dominant. And whereas 3 and 4 dominating, so itself and then 4. Whereas 4 dominates, that is 5, 6, 7. So node 4, what is the node 4 dominating? All 1, 2, 3. Except 1, 2, 3, node 4 dominating, that is 5, 6, 7, 8, 9, 10. All dominating. But 1, 2, 3. So since all pass from 1, must begin with 1 only. So 1 to 2, then 3 to 4, or 1, 3, 4. Either of them we can write. So the 1 dominate 2, then 3 dominate 4, 1 dominate 3, 3 dominate 4. Like this we can switch over 1 to 2 or 3 to 4 or 1, 3, 4 we can switch over. So that is to be represented here 1, 3, 4. This is the structure to be represented, this dominated tree. And then node 5, 6 automatically dominates every node itself, and the flow of the control is skipped by going through the other nodes. Node 7, which dominates 7, 8, 9, 10. Node dominates 7 itself, and 8, and then 9, and then 10. Whereas 8 dominates 8 itself and then 9, 10. Like 7 dominates 7, 8, 9, 10. Node 9, 10. Node 9, 10 both are dominating itself. So that's why I have 7. Node 9 dominates itself, node 10 dominates. So like that we are going to write a tree notation represent where one node dominates another node. Then this form of tree representation is called as Dominator tree representation. This node representation is done. Since here we are going to verify the definition, if every path from the initial node of the flow graph node goes to the n with the through D, then we can say that D is dominator with n. So that is represented by D dom n. So in this case, 1 is the initial node that goes to the dominated node. So 1 is dominated itself, whereas node 2 is dominated itself, and then control is reached to other path that begins with 1. So that's why here the 1, 3, and where 3 dominates itself, but 1 except that is 1, 2. Node 4, 1, 2, 3 dominates itself. Node 5, 6 itself, and control flow goes 7, 7, 8, 9, 10, and node 8 dominates 8, 9, 10, and node 9 dominates itself, node 10 dominates. So that's the representation where we have been used this node and edge. So this 1, 2, 3 are called nodes, and these are called as edges. This lines represents edges, and the circle notation represents nodes. So these are the two things which are to be used inside this flow graph representation, and we are going to implement this dominator structure, and we are going to write a separate tree structure where this is to be involved. And the way of representing this dominator information in a tree, it is called as dominator tree. Here in this tree, initial node is the root node, and the parent of each other node is its immediate dominator. Each node D dominates only its descendants in the tree. That means here we are going to verify that node is dominating any other node in n. So that is to be compared with the immediate other node, and we are going to take the parent of each and every node. If any dominates tree takes place for that child representation, then that is to be happened only with the descendant of the tree, not the root of that. Some of the loops which I have discussed, one of the loop structure that is natural loops. Here one application of Dominator information is determining the loops of a flow graph which is suited for the improvement. What are the different properties of loops? Every loop which contains a single entry point, that is called as header. One of the point here it is, while when considering the loop structures, any statements which are there inside the loop, we are going to repeat that statement several times until condition is true. If at all, if the statements are trying to execute, then the entry point for that loop structure is only one time, that is called single entry point, that is to be noted with a separate notation that is called as header. And we are saying that this is the Dominator with all the nodes which are, suppose if one loop which contains that is header structure with some link of statements, another loop structures which are to be there with other loops also, then this is to be case as the dominates remaining other nodes in the loop of the entry structure. That means it is not the sole entry of the loop. We can say that there is only one entry to iterate the list of instructions, or at least only one path which is leads to the back to the header point. That means we are going to move to the again re back to the previous node. Then that is the only entry point. And one of the point here is finding out all the loops in a flow graph, that is searching for the edges. We have to search for the what are the edges that are available from one node to another node inside the flow graph, and we are going to determine what are the heads and what are the tails. How can I determine the heads and tails? Suppose if there is a node A and if there is a node B and there is an edge belongs from node A to B, then we can say that B is the header and A is the tail. If there are two nodes which belongs to A and B, then if there is a transition edge exists, that means the link exists between the two nodes, then we can say that a tail and head process notation, where in this case B is the head and T is the tail. These type of edges are called as back edges. These edges are called as back edges. For example, in the graph which is shown previously, that is 1 determines with 2, 3, and 3 is determined with 4, 5, 6, and 7, 8, 9, 10, like this, the Dominator tree. Some of the graph, the edges with the dominance, that is 7 edge, suppose 7, 4, then there is a transition from 7 to 4. So here we are going in this, as per this requirement, who is the head, B is the head and A is the tail. So here if you consider A with B, there is a transition, then as per this, A is the tail, B is the header. So B4 is header and 7 is tail. And D dom N we are going to represent, that is which is the Dominator, 4 dom 7. So where is the arrow mark shown to this point? This is the header. So that's why 4 dominates 7. Similarly, 10 to 7, if it is an edge, 7, we can say that 7 dom 10. So like this 4, 3, 8, 3. So in this example, in this graph, Dominator tree, 1, 3 is structure, 3 is the head if that points, then that is 3 is dominates 1. Are the loop edges which are forming the loop, back edges with the represented as N arrow mark D. This represents there is a edge which belongs to the D. So this n arrow mark D represents D dom n, where D is dominated with the corresponding D, n. That means here the edge to the D plus set of nodes which are reaching the without going to the through node D. So node D is the header of the corresponding loop, where the node D, which is the header of the corresponding. Why? Because it is the head pointer and it is the tail. Where the arrow points to this, that is head, and where is the other is tail. Another important one is inner loop, where the loop of statements, group of block of statements are to be repeated. That is called as inner loops. It is one of the useful property where the same header with the same two loops, same header, they are either disjoint or entirely contained nested inside another loop. That means one loop contains no other loop. When two natural loops have the same header, so previously we told that whenever an entry point which is available, that is called as header. And but neither is nested within the other, they are combined and treated as a single loop. That means if they are having the same entry point, then that is to be considered as blocks of the statements and to be combined. Several transformations require us to move the statements before the header. That means before beginning statement, the loop creating any new blocks are there. That is to be considered as pre-header. So before starting, some of the statements you can kept it. That is here, for example, this before the loop executes, and before this loop, some of the statements we are going to make. So that statements are to be placed inside a pre-header. So it is only the header as successor. Pre-header is a header as successor, and all the edges which are formerly entered header of L from outside L enter the pre-header. What are the statements which are to be written? That is to be entered to the header of L from outside L. Edges from the inside the loop to the header are not changed. Initially, pre-header is empty. That means we don't put any statements inside the pre-header. But the transformation and L may place the statements in it. Some of the statements which are to be considered want to place, that is to be moved outside the loop and placed inside the pre-header. And reducible flow graphs is the one of the mechanism which is used to representation for the purpose of these loops, and this where the reduction takes place. For example, unambiguously defined entries and dominators and these data flow analysis problems, and all these things can be easily solved with the help of this reducible flow graph. And the structured flow graph statements such as if then else, while structure, continue, break statements, and these are all is used to reduce some of the flows inside this mechanism flow graph structures. And the most important properties of reducible flow graph structures are no jumps are to be in the middle of the loop from outside of the loop structure. There will be no jumps in the middle of the loops, and there is only one entry into the loop structure, that is to be represented as header. We are not going to keep several headers, only one headers. If at all, if there are more entries, and try to identify and combine that into a single header in the previous video discussion. A flow graph is to be represented, that is to be considered as a reducible if and only if we are going to partition the edges into two disjoint groups, that is forward edges and another one is backward edges. And this having some property that forward edges forms an acyclic graph in which every node can be reached from the initial node of G, whereas back edges consists of only edges whose heads dominates the tail. So previously I have seen how the edge dominates tail. So that is to be considered as back edges, and forward edges to be considered as, which is to be considered acyclic graph. So acyclic graph means every node is reaching from the initial node, reached from the initial node of the given graph. So here in this, we are going to see that a non-reducible flow graph for the given flow graph. Here we are going to set a loop which must contain a back edge. So here in this loop consists of node 2 and 3. There is no back edge. So it is a not non-reducible flow graph. Why? Because there is no back edge. Consists of node 2 and 3, and but there is no back edge. Back edge means here, if at all, if that back edge consists of back edges, heads which dominates tails, that is to be considered. So that is as a separate reducible flow graph or non-reducible. So here, if that property is not satisfied, reducible property. Not satisfied, that's why it is considered as a non-reducible flow graph. It is considered as a non-reducible flow graph. But in the side graph, if it is showing in this graph, if you show that if you remove some of the edges, 4, 3, this is a back edge, this is also back edge, 7, 4, 8 to 3 is back edge, 9, 1, 10, 7. These are all all back edges. Then removing the forward edges, and this forms acyclic graph. That means whenever you remove that 4, 3, 4, 3 and 7, 4 and 8, 3, 9, 1, 10, 7. So if at all, if you remove these back edges, these are all back edges. That means back to the, this, we know back edges previously was shown. That means that edge is to be identified and removed, and the remaining edges forms as acyclic graph. Yes, then we can say it is a reducible graph. So the acyclic graph which does not contain any cycle. So here in this graph it is cycle. So if you eliminate one like this, then there is no form of, there is forms cycle. So here in itself it is form the cycle. So it is as a, if not formed, then we can say it is. So 3 to 4, 4, 5, 6, and then 7 node, and then 7 to 8, and 8 to 10, and 8 to 9. Up to this we are having. Remaining edges are all removed. Remaining edges are all removed from this previous one. So here in this case, we are going to remove remaining all forward edges forms. After removing all these back edges, the remaining forward edges forms acyclic graph. Hence, it is reducible. If it is reducible, then we can say that it is a reducible flow graph. So in this case, it is a reducible flow graph. So like this, we are going to identify the edges, back edges and forward edges. If at all forward edges forms acyclic graph, then this property is satisfied. So that it is a reducible flow graph. Hence, if it is not satisfied, it is not reducible. So any of the property which holds this property of forward edges or backward edges, then the both holds satisfying the properties. Else any of them deviates also non-reducible. So by taking this second property, back edges, so non-reducible following, that is, it is a non-reducible flow graph. Left side, why? Because there is no back edge. There is no back edge from this flow graph. So one is the edge which forms to that node 2, and from that one which is forms to the node 2, and from node 2 this 3 node 3, and from 3 2. That means there is no back edges. Whereas If we consider here, so many back edges are there. 4 3, 4 3 is a back edge, 7 4 is a back edge, 8 3 is a back edge, 9 1, 10 7. These are all to be considered as back edges. So all these to be identified, and then we are going to be in that. So reducible flow graphs, which are to be very much used for the purpose of unambiguously defined entries, are there. That is to be dominated with any other entries that are calculated, and much used problems are data flow analysis problems, which are to be efficiently solved. And some of the statements such as if then statement, while, continue, break statements, all these are all very reducible, non-reducible flow graphs. And any jumps which are there inside that the middle of the loop and keeps outside of that loop, and any entry points which are headers, that is to be considered, and any headers which are more than one, that is to be combined into a merged into a single one, and pre-headers are to be taken place. So here the statements which are there inside the loop, the statements which are to be considered and move to the out and name it as a separate block, that is called as pre-header, and then this is to be matched into entry of the loop, that is header point. So previously a loop statement with header with the entry, but now it is to be entry into another one. So with the statements are to be identified which are there inside that one, that is to be moved outside of the loop structure. So P header is as only the header as successor, and all the edges which are formed entered the header of L from outside L. Instead enter the pre-header. So like this, any statements which are inside the loop, so that the header process does not change. Initially pre-header does not contain any statements. Now we move some of the statements, but this transformation doesn't affect any of the other things. So that's why keeping the statements and making the pre-headers, it is an important task in case of this one. So that after that we make a flow graph notation. If the flow graph notations are to be applied with the several structures, flow graph control structures, if statements, while, continue, and jump statements. With this concept, we know that what are the edges that are to be back edges and what are the edges that are to be forward edges identified, and then if any rule satisfies the DA, then it is considered as a reducible flow graph. If any of the rule doesn't deviates, then it is not a reducible flow graph. So that we are going to use this as a separate notations in case of compilers and structures. We will come up with thank you once again. Thank you. We will come up with one more new topic from the next subject. Thank you. In this same subject, next topic will come. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.